This is very, 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 very similar to 10.1, except for instead of two proportions, we got two sample means. And that's it. We're going to go through the same process. We'll look at the shape, center, and spread of the difference of two sample means. We'll look at how to meet the conditions. It's the same as it was for confidence intervals for one mean, which is also the same as it was for when we were doing inference on one sample mean from a population. So we'll look at confidence intervals, we'll look at significance tests, and see when we would want to do this. So we'll be looking at a t-distribution as we go through this. So we wanted to compare the mean of something for two populations. Our parameters are going to be mu sub 1 and mu sub 2. We'll have two separate samples. We'll compare the sample means. The way that we're going to compare these sample means is we're going to look at the difference of the two sample means, right? Almost exactly the same thing as we were looking at before. Just different notation. So there's this U.S. National Health and Nutrition Examination Survey. They look at the heights of 10-year-old girls. Interestingly enough, it looks like the mean height of 10-year-old girls is larger than the mean height of 10-year-old boys, right? And remember, we read this as saying that it's a normal distribution with a mean of 56.4, standard deviation of 2.7. Right? This reads as saying the distribution of heights of these 10-year-old males is approximately normal with a mean of 55.7 and a standard deviation of 3.8. That's how we read that. So that's why I was able to get that information. It looks like the mean height of 10-year-old girls is larger than the mean height of 10-year-old boys. So we take a simple random sample of 12 girls and 8 boys, and we measure their heights. We would be able to find the mean of these 12 females and the mean of these 8 males and compare them. So it should be the case, right, that the difference, x bar sub f, right, the sample mean of these 12 females minus the sample mean of these 8 boys, we would expect it to be positive, right? If indeed 10-year-old females are on average taller than 10-year-old males. I don't know why they use girls and boys here than male and females. Just mess them all up. All right. So if they were to generate simple random samples of 12 girls and 8 boys from a normal population 1,000 times, this is what the distributions are going to look like. The thing that we're mainly interested in looking at is this one over here on the far right, where we're looking at the difference in means is 0.67, and our spread, or standard deviation, is 1.58. And 1.56, sorry. I'm looking at where do these numbers come from? So, right, if we're going to describe this distribution, remember we look at shape, center, spread, and any possible outliers. Probably not going to be huge outliers if you're going to take a sample size of 1,000. It's going to be hard to really get an outlier out there. So we've described the shape, center, and spread. It's approximately normal, and we talked about center and spread. Okay. So same rules apply when we were talking about random variables way back a long time ago. If we want to know the mean of one random variable x minus one random variable y, It's just the mean of random variable x minus the mean of random variable y. Our standard deviation, though, right? Remember that was weird? Standard deviation of random variable x minus random variable, or rather the variance of random variable x minus random variable y is just, you're going to actually add those two standard deviations. Or two variances, sorry. And then take the square root in order to find the standard deviation. So, if we're going to describe the shape, center, and spread of the distribution of random variable x minus random variable y, if the populations are normal, then the sampling distribution of your sample mean minus your second sample mean is going to be normal. Otherwise, you're going to have to check that the sample sizes are large. And you have to check each one individually, right? It's not good enough for one or the other to meet the condition that their sample sizes are larger than 30. They both must be larger than 30 in order to assume that the distribution of the sampling distribution of their differences is going to be approximate. The mean, quite simple. You're going to be able to just take the mean of one minus the other. And then this spread, your standard deviation of the sampling distribution of your difference of sample means is going to be found according to that formula, where you'll find the variance of the one sample divided by the sample size plus the variance of the other sample divided by sample size. Take the square root of that whole thing. Good news, that formula is on your formula sheet. I'll show you where it is. So if you look at your formula sheet, you will find back over yonder, boom, two sample, right? Difference of sample means there's your standard deviation right there. It is so very rare that your standard deviations are going to be the same for two separate samples. This special case is, you might as well just stick with this. Stick with that. All right. This is what the sampling distribution looks like. Whatever. All right. So you guys have this formula still. If we're looking at a t-statistic. In order to calculate the standard deviation, we are going to have to make sure that the 10% condition is met. And then if the normal condition is met, we can get a t-statistic. Show you the formula for that. Shakalaka. There's our t-statistic. The majority of the time, our parameter value that we're going to be using, let's have this mu sub 1 minus mu sub 2. The majority of the time, we're going to assume that parameter value is 0. Especially when you do it. Not every time, but like I was going to say, the majority of the time, you're going to assume that your population mean, the difference, I should say, of your population means is going to be 0. And then we'll compare that to the difference in our sample means, our actual differences. No, I think. All right. So also an important thing on this is when we're going to decide on degrees of freedom. You're going to use the smaller one. So in the case with the females and the males, right? We took a sample size of 12 females. We took a sample of 8 males. So the degrees of freedom that we're going to go for is going to be the 8 minus 1 degrees of freedom. So we'll go with 7 degrees of freedom. And not the 11 degrees of freedom. So take the lower sample size, subtract 1. That is going to be your degrees of freedom that you'll use. All right, so in order to check your conditions for performing inference about the difference of 2 sample means. So inference about the inference about 2 population means, right? We'll use 2 sample means in order to perform that test, or whatever test you're going to use. Again, the data has to come from a random sample. You got to check your 10% conditions for both samples. Okay, both samples. You need to meet that. And then the sample has to be large enough. If the sample size is less than 30, you're going to have to graph the sample of both. And then make a statement of why each of those can be assumed that they're approximately normal, right? There are no outliers, no extreme skewness in the data. All right, so here we go. Confidence interval. To approximate where the difference of the 2 means of 2 populations are, looks just like this. Pretty much follows that same formula that we were using for doing a confidence interval for a population mean. Only difference is, right, our point estimate is just the difference of the 2 sample means, and our standard deviation is going to be the standard deviation of the 2 sample means. Remember, for that t star value, we'll use t distribution table, and the degrees of freedom will always go with the smaller of the samples. So you calculate the degrees of freedom.
How do you know when it's plus or minus?
How do you know what?
Do both. When it says plus or minus?
You must do both for plus or minus, right? The minus gives you the lower bound of your confidence interval, and adding gives you the upper bound.
Yeah.
All right. So if we're going to do a significance test for hypothesis inference, our null hypothesis is going to be parameter 1 minus parameter 2 equals some hypothesis value. If there's, we want to usually hypothesize that there's no change, right? Which means that our null hypothesis is going to be that the mean of population 1 minus the mean of population 2 is 0. More often than not, that's what we're going to be doing. That's what our null hypothesis is. That the difference of the 2 means is 0. I'm not a huge fan of this null hypothesis that the means are the same. I like this one for the same reason that I liked it with our difference of proportions, is that when I get a t statistic, I can just plug in 0 in there. It's nice. And I'll show you where. I'll show you what I'm talking about. And then our options for our alternative hypotheses are going to be that the difference is greater than 0, the difference is less than 0, or that the difference is not 0, right? That there is actually a difference, whether it's greater or less than. This lady is getting huge.
Yeah.
I'm essentially doing like one-legged squats. All right. And this is what I'm talking about, right? So if your null hypothesis is that mu sub 1 minus mu sub 2 is 0, then right here, you are always going to input 0. It's kind of nice. I like it like that. It's less stuff to remember. And then you guys already know how to find the p-value, and then make a decision. And we'll work some of these next class. Same formulas that you had there. This is exactly the same stuff we want. Except for we now have pictures of the one-tailed hypotheses and the two-tailed. Okay, so we're going to go with 2 sample procedures. Also, I'll show you how to do this on your calculator. Your calculator will spit one of these out for you, just like that. It also gives you some clues as to how to input things into the formula. So it's really nice. The calculator will help you a lot with this. So if you can, choose equal sample sizes, right? You don't want to fool them, so don't add the 2 means together. It's just weird. I'm not sure why you would think to fool them, but it's there. It doesn't want you to do the same thing you were doing. How you had some that piece of C in your proportions, difference of proportions, where you were adding your numerators and your denominators and having that full value. It doesn't want you to do all right. So if you have paired data, don't use it. So some sort of matched pairs design, don't use the 2 samples. You can just look at the distribution of the difference of the sample means is kind of one thing instead of having a mean. And that's it. Make sure that there's randomization. And that's it. So we did all these things today. Looked at the sampling distribution of 2 sample means. Found what conditions need to be met. Looked at how to construct the confidence interval. And all of these things we'll do in context. We'll do some actual problems next class. And then we'll have this one done. Yeah, I haven't.